Hello there. Today we're going to focus on extending your Newton-Raphson method, which is a very fast way of finding the root of a single function, to 2 dimensions and higher dimensions. And it turns out that this method is very useful, not just for finding roots, but will turn out for finding other things like minimization of big functions. So we're sort of moving our methods from sort of simple 1D examples that you've done in the past to multiple dimensions. Okay, so I'll just leave you now to the board. Okay, bye. Okay, so we're looking now at higher dimensional Newton-Raphson, higher dimensional Newton-Raphson. You are. And we're going to focus on 2D. As often the case, 2D is very useful for working things out by hand, understanding the method works. But we must remember that the applications eventually are going to be in much higher dimensions. That's where it comes in. So what we're doing is we're going to extend our 1D method. So to recall, in 1D, we found the root of a single 1D function. Okay, so that was f of x. Okay, all very easy. So in 2D, we want to extend that. In 2D, we seek the roots now, more than one root, of 2 2D functions. And that's the key thing. It's not just going to a 2D function, say f of x of y, and finding the root of that. That doesn't make sense, actually, if you think about it. You need, for the problem to be completely constrained, you need 2 2D functions. So we're going to have f of x of y and g of x of y. So we're finding this solution to this problem. Okay, so that's the key idea. Let me just show you the MATLAB figure from the notes. So let's just clear the board, go to the screen, get our MATLAB up. Okay, so here's our MATLAB. And in MATLAB here, I've got 2 functions, one for f and one for g. I've defined them. One's a quartic, I'll come back to that in a minute, and one's a quadratic. Sorry, that's a correction. This is where these are the functions where the roots lie. So if you like, if you have 2 functions, that are quadratic, one's a quadratic and one's a quartic, say in x and y, the places where they intersect is going to form a function of one variable. So that's the point here. This is why we need 2 functions. So let me just run it again. So we basically constrain the function. So if we constrain f of x of y as 0, that's still a function, right? Of one variable, and that's shown by the solid line here. And the g of x of y is 0 is still going to be a function. So that's why you can't have the function on their own. You just have f of x, y is 0. And when these 2 curves intersect, you get the 2 roots you're interested in. So now, whilst with the 1D example, we had a single root. Now we have a 2D problem. We have 2 roots. So just correct what I said earlier then. y of f is just the function where f of x is 0, and y of g is where g of x of y is 0. So it's a function rather than an actual single value, and you have to find the intersection of these two curves to find the two roots. So this is just where we're going. This is why we need two functions in two variables, and we're going to have two solutions for that. So that's just to put in context. If that will make more sense when we get to the end, but I just wanted to show you that now as motivation for the for two variables. Okay, so it's convenient to write it down in terms of vectors. So we're going to define a vector. I'm going to call it big F, that contains our 2D function, so f of x of y, f of x of y, and g of x of y. Okay. So if we can write it in terms of vectors, then we can form the analog, then a direct analog of the 1D method of Newton-Raphson. So our 2D function, vector big F x n. So x of our big vector x of n is just a state of x n and y n at 2 points. So you put x n and y into a vector as well, and the f of x of n is the value of these functions f of x and y at two values. So that will be a vector which contains f of x of n, y of n, and g of x of n and y of n. Okay, so that's going to be a key mechanism. So with these vector quantities, we can now define 2D Newton-Raphson. Okay, so that's what we're going to do in the next slide. So here we go. I'm just going to write it down, and then we should be able to see the links with the 1D method. So we're now iterating two functions. So we have f at xn plus 1, yn plus 1, and g of xn plus 1, yn plus 1. Okay. Equals, I'm going to write this in the new line, f of x of n, y of n, g of x of n, y of n. Okay, so then we're iterating the function at the new value of xn plus 1 is the old one. So this is essentially what I'm writing down is a Taylor expansion, really, but maybe in a different way. So this is a Taylor expansion we're doing, but in a different form. So we're finding the function value at the new point, xn plus 1, in terms of the function value of the old point, and we're writing down in terms of vectors. So I'm writing out in component form first, and then I will collapse it down into vectors, and then the analogy with the 1D Newton-Raphson will become clearer. So this then is your function, vector function at step x of n, right? And that would be the other one would be your so then we have to introduce the gradients in this problem. So in in 1D you just had the df by dx, f prime. But now we're going to have the possibility, we've got two functions of two variables. So for each function, we're going to have two derivatives, right? df by dx, df by dy, and then dg by dx and dg by dy. So all those things need to go into a matrix, a 2 by 2 matrix. That's 4 derivatives. And it's partial f by dx, partial f by dy on the top row, and then dg by dx and dg by dy. And you may have come across this thing before. It's called the Jacobian. This is slightly different context probably than before, and we're going to call this j of x of m. Right, so this thing I'm doing here, I'm putting a vector in a function. That's completely legitimate. All it is really shorthand for putting xn and yn into the argument. So you've probably seen f of x of y. Well, actually a shorthand for doing this, and we'll be using this sort of shorthand before, is the same. So this is a big vector of xn vector, and you could read it longhand as a function of x and y if you're concerned. So and then we've got xn plus 1 minus xn on the top, and then yn plus 1 minus yn. And because we're looking for the root, we're looking for the zeros, this equals zeros. Okay. Okay, so that last bit is saying we're finding the roots of these functions. We're looking at the root. So, but the key points here are that you've got your Jacobian, your change of xn plus 1 minus xn, and then you've got your function of xn. So this is not the Newton-Raphson at the moment. This is a Taylor expansion in terms of vector, which contain your functions f and g. But this is the way we derive the 2D or any dimensional Newton-Raphson method. Okay, so we're finding the new value of the function at point n plus 1 in terms of the function at the old point xn plus 1. And what we need to do then is rearrange using our vectors, calculus and our matrices knowledge to get xn plus 1 in terms of xn, yn plus 1 in terms of yn. Okay. Okay, so we need to rearrange this Taylor series. So we have xn plus 1, yn plus 1 equals something. Of course, the shorthand for xn plus 1 and yn plus 1 now is x vector m plus 1. Okay. Okay, so when you do this rearrangement, the key thing to do from before is that you had the Jacobian, you need to multiply through by the inverse. So you multiply by the inverse of your Jacobian, j minus 1. Okay, and then that will give you this expression, which is xn plus 1 equals, this is x vector now, so that contains x and y, equals xn minus Jacobian of x of n times f vector x of n. Okay, so what we have here then is a direct analogue then of your 1D Newton-Raphson. In fact, this will reduce down to, if you made this the 1D version of this, you had a 1D vector, 1D matrix, which is just a derivative, then you get the same value. So this is the analogue of 1D Newton-Raphson, where we had xn plus 1 equals x of n minus f of x of n divided by f prime x of n. So if we just work from the left to the right, we have xn plus 1 scalar value corresponds to the vector now of x and y. So when we're iterating now, we're starting with a certain value of x and y, certain value on the x, y position, and then we're finding a new value according to our methods. So that's there, and then you have xn scalar, it corresponds to xn vector scalar. And then we have the inverse now of the Jacobian. That corresponds to 1 over f of x of n. Okay, let me just circle those two things. So you have j of x of n here, j prime of x of n, and then you have 1 over x of n. So they are directly corresponding. And then obviously you have big f of x of n as well. I'll do a dashed line to that without making my things too messy. Corresponds to your big f of x of n. So it's directly analogous. But now, whereas we were just evaluating the derivative each time, we now have to evaluate the Jacobian each time and find its inverse and multiply it through a vector. So it's a little bit more involved computationally. But this is this method of finding the answer to your solution, in this case we're finding the root, is very applicable to a whole lot of problems. In fact, we'll come back to this type of problem when we do optimization at the end of the course. So you know, this idea you're navigating round. So let me just draw a picture of how that works. You're going to be working in so we know that in x and y there's two roots that exist, and obviously the Newton-Raphson will converge to the one that's typically closest to it. That's normally how it does. So you will have your sort of starting point, your sort of x naught, y naught, and then each step of your iteration you will navigate around this xy plane. So x1, y1 could be there, for example, and you're moving towards the root. Okay, so that's the way it works, and you're using the Jacobian, this matrix of gradients to navigate there. Okay, I think what I want to do is go through a MATLAB example. That's going to take me over the sort of 20-minute limit that we're kind of setting ourselves for these videos. So I'm going to sign off here and see you in the next video. Okay, bye for now.